Welcome to Azim PMG University.
Thank you for your invitation. Yeah.
Thank you, sir. We are interested to know how your journey as a researcher started and what inspired you to become a polymer scientist.
I don't think I really planned my life in a way that it has turned out. I think my interest in chemistry deepened during my master's in IIT Bombay. Till then, I think I was unfocused. I think the learning experience in IIT Bombay was certainly something that got me interested in research. The teaching as well as the nature of learning changed from the university where I studied earlier, and at IIT it was. So I think, and that is a period also that gave me some confidence about my own abilities to pursue research. So that was it. And polymers, I think I was inspired by one of my teachers at IIT Bombay. His name was Gaddam Babu, who also left and joined 3M subsequently. So he was a teacher, and also I wanted to do my master's project with him. So I was focused in polymers right from my MSc, and so that's what took me to polymer science. Yeah.
Interesting, sir. Thank you. And being a researcher, always come with its own challenges, right? So what are the challenges you faced as a researcher, and what are the ways what are the paths you took to overcome those challenges?
Well, challenges in research are very similar to challenges anywhere else, correct? After my PhD, I worked for a couple of years as a postdoc in an industry. It was a very unique experience, which I enjoyed thoroughly. And then I came to IISc to start my career as an independent researcher. And the plans that you have when you come back is with an expectation that the infrastructure, etc., will sort of be adequate to perform those kinds of research. So I think somebody once asked me about a Schlenk line. And in fact, I had a Schlenk line which I brought with me from the US, thanks to my company's generosity, and wanted to do experiments which are air sensitive, water sensitive, and so on. So, but I had to give it up quickly in the early days because of the absence of that. So I moved on to things that are easier to do on a lab bench. So I shifted. So I think in general, to answer your question very broadly, the challenges that you face are many-fold, right? Like we face in anywhere else. It is our own strength that generally ensures that you're not bogged down by the challenges, but you find ways to adapt rather than always trying to overcome. So I think that's probably what I did, and charted a direction for research that did not require the kinds of things that I had in mind when I started. So, and that's been my strategy. I think it's always, you'll find a way out of situations that challenge you.
Thank you, sir. It will help us actually to move forward with all these, challenges whenever we face. The next thing I would be actually, interested to know is, you have been doing research since 1990s. I mean, even as a PhD student, but after getting into IISc, pioneering work at polymer science. So what is that one research as per you is close to your heart, and it contributed to the field of chemistry the most, and why?
That's probably the hardest question to ask a faculty, a researcher in general, I would say. I say this only because, as a researcher, we all fall in love with the research problems that we select. And I wouldn't be able to pick one probably most interesting problem. I might say that there would be 3 or 4 phases in my career. At each of these have been very satisfying to me as posing the problem, designing a strategy to address it, and finding that at the end of it, you've actually answered it. So in that sense, I would say one of the early problems that we worked on was on conjugated polymers. And there what we were interested in is to devise a method to control the average conjugation length. It was well known that a lot of properties of conjugated polymers are related to the conjugation length, which is the number of p orbitals that are in continuous conjugation. So to address that, we developed an interesting method by which you can vary, although in a statistical manner, you can vary the average distribution of conjugation lengths. And what we did was to start off with a precursor, which is not conjugated at all, and install thermally eliminatable units in a statistically random fashion. We selected two types of units, one of which was more easily eliminatable and the other was far harder to eliminate or even not eliminatable. So by just changing the relative population of the eliminatable and non-eliminatable units, which are randomly placed, once you remove the eliminatable units, you create a conjugated backbone. So by changing the relative populations of the non-conjugatable, non-eliminatable units, you can control the average conjugation length. So we estimated, we also, I might say, computed what the expected properties would be. And we developed a very nice correlation between the spectroscopic properties and the average conjugation length, although we didn't do any other property measurements such as conductivity and so on. That was one of the very interesting problems. The second problem relates to a second field, which is the area of hyperbranched polymers, which we've been working on for almost the entire career I have spent at IISc. And there, I think one of the fundamental questions that we designed to address was that hyperbranched polymers are like trees, which means it sort of periodically branches, continuously branch upon branch. Very similar to dendrimers, but it has a large number of linear defects. And the property of hyperbranched polymers is that they adopt a very compact structure. So the volume, the hydrodynamic volume of a hyperbranched polymer of a particular molecular weight is far smaller than the analogous linear chain of the same molecular weight. So the question that we were interested in addressing is to ask, how is that property, that compactness, influenced by the length of the segment that lies between two branching points? And that we address very carefully by designing a set of monomers that prepares that, when polymerized, yielded polymers where the length of the segment between adjacent branching points continuously increase. And then we measured the properties, and what we were interested in correlating was the Markov exponent. That means the intrinsic viscosity varies as an exponent of the molecular weight. So molecular weight scaled to some exponent. The smaller that exponent, the more compact the chain is. So we showed that the exponent increases from something like 0.3 for a very compact chain. As the length of the segment increases, it goes towards 2 by 3, which is 0.66, showing that once the segment is fairly long, the hyperbranch polymer loses that property of compactness. So that was again a fundamental correlation. We developed another nice experiment that I like. And more recently, we've been interested in controlling conformations of polymer chains in solution. And we all know that given an opportunity, polymer chains will adopt a random coil because the entropy of a random coil is far higher than that of any other structured coil. The question is, how does one develop strategies like biology does? Biology does it in terrific ways. But how do we mimic those ideas in synthetic systems and develop a method to control conformation of polymer chains in solution? For that, we selected several weak non-covalent interactions that would collaborate and synergistically support one specific folded form. So for that, we used effectively three interactions. One is the crown ether type interactions of an alkali metal ion with a oligoxyethylene unit. And then we used hydrophobic exclusion. That means you create a system, a polymer which has hydrophilic PEG segments and hydrophobic aromatic units placed in an alternating fashion, which will co-locate the hydrophobic units together and will envelope that with the hydrophilic PEG segments. And then because the metal ion coordinates with the loop, it brings the donor and acceptor in close proximity that enables the charge transfer interaction, which is the third interactions we had. So these three together enable the polymer chain, which otherwise would have adopted a random coil to form a pleated structure like this, And more recently, we are excited about developing a completely alternate method. We call it immiscibility-driven folding, which means if you think of a chain that has, let's say it's a hydrophobic chain like polyethylene, and you install at periodic intervals. When I say periodic, the length between the point at which one anchoring is there and the other is exactly the same. So it's a graft polymer, but it's called periodically grafted, and it's amphiphilic because the nature of the segment grafted is completely different from the nature of the segment on the backbone. So let's say this is hydrophobic and you have a hydrophilic PEG segment installed at periodic intervals. Now this chain, when you take it in water, because the hydrophobic segments like to exclude water like micellization of a surfactant, what it does is it folds in a zigzag fashion that brings all the hydrophobic segments at the center. It collapses it into a cylinder and presents the hydrophilic PEG segments on either side. So this co-location of the hydrophobes in the middle and hydrophilic PEG segments on either can be assisted if the length of the hydrocarbon segment is very long, then it tends to crystallize. So we showed that if you take this polymer in water, it co-locates driven by the same forces that micelles are formed with surfactants. And then the hydrocarbon segments actually crystallize in a paraffinic lattice. And you can measure the melting point associated with the hydrophobic crystal formation. So in fact, if you take an aqueous dispersion of this in water and measure the DSE of a solution, you can actually see the melting associated with the hydrocarbon. So which means the enthalpy released as a result of crystallization stabilizes the folded form. And then these organize into lamellar ordering in the solid state. So this last part has been the most interesting thing that we discovered recently. And we have now most recently sort of shown that by installing photoreactive groups in the middle of the hydrophobic segment, once it collapses, you can actually cross-stitch it by shining light, which means you take a chain, you fold it, and then you stitch it this way so that the folded thing is now a particle, becomes a particle. So that's something that's given us a lot of pleasure more recently. Apart from that, we've dwelled on lots of other interesting problems, but I think, that's for a different day. Go.
Amazing. As a polymer chemist, I would be more interested to know, what polymerization techniques you use. Like, is it addition or what should be the carbon length for it to, crystallize and all those things. You mentioned about hyperbranch polymers or, conjugated polymers. They have enormous, real life applications. So I would be more curious to know, your personal anecdotes and how your personal research you try to integrate with the social requirements or for social causes.
Yeah, this is a hard question. I think my research, that is my research interests and how it has impacted or contributed to societal causes would be effectively nil, because I have not directed my research in a manner that the outcomes will have impact on social causes. But I would say as a teacher and as somebody who is a mentor for PhD students who carry out research, I think the social impact of our own work will probably be more in the form of contribution to the I would say to the skills in teaching and research that my students would carry across the country. So the impact that my research or my own career would have had is probably more through my wonderful students whom we have graduated over the last 30 years and how they would contribute to educating more people and training more students. So that would be my take. I've had consulting, I've had consultancy contracts with companies, but that's again basically building competency at various companies and assisting them in their own research, but not direct impact at all. Yeah.
Indirect impact is also very much needed. Just as a continuation of the same question, see, we know nowadays everywhere say no to plastics, right? Boards. And we know we cannot live without plastics or polymers either. I mean, we also know that polymer pollution is not the top polluting, industry in the world. But still, I would be curious, to take your opinion on how we as polymer scientists can help in, or come up with polymer innovations that would solve these environmental problems like, microplastics or microbeads, which are found in water bottles, or plastic pollution everywhere from the aesthetics point of view. So please throw some light on.
This is a question that we as practicing polymer scientists are always faced with. The issue of plastics is actually something of the talk that I would give on. But my take on this is primarily that much of the problems, like in many cases associated with plastic pollution, has to do with the behavior of people. The plastics itself don't contribute to environmental damage as much as the responsibility is of the user. So we have been the cause of much of the problems we've created in the context of plastics. For instance, let's take polyethylene, which is right up there in the contaminants that we see. We have gotten used to using plastic packaging very extensively, and the quality of the plastic bags that we get have steadily made it thinner and thinner because it's less use of plastic for a certain purpose, right? And that has caused these things to become essentially not collectible in an easy way. I would say mechanically fragmentable very easily. And it leads to, when mechanical aberration and this happens to plastic material, it leads to generation of small amounts of tiny particles. So, for instance, in another context where since you said microplastic, so there is plastic pollution is one aspect when you look at macroscopic objects, which are probably a little easier to solve once you discipline the user. You have methods to collect it and then reprocess. So the good thing about plastics, many of them, especially the virgin plastics, which means you don't have much added to it, like PET and polyethylene packaging materials. These are actually almost completely pure hydrocarbon. And in case of polyethylene terephthalate or polyester. So once you collect them, these are actually not very hard to reprocess. However, the microplastics that you spoke about, those are very tiny particles. One of the big sources of that is the tires. So what happens is, we want the discovery of rubber tires is probably one of the most important discoveries of the last century. However, what happens when you have tires? Tires need to grip the road. That's the function of a tire. But when it grips the road, it grips it because of friction. So as a result, whenever the tire is running on the road, you notice also that it abrades, right? So it generates very fine, tiny particles that kick up in the air. So much of the plastic pollution, microplastic pollution, happens as a result of abrasive. And those are actually far harder to deal with, okay? Because you need the rubber tire. At the same time, you need friction to be able to run it effectively. At the same time, you have to avoid. So that is a challenge, and I'm not sure how we are going to address that. It's going to be something that would need some very interesting new innovation to be able to have the gripping ability At the same time, be able to not allow those things to get into the water and other streams, air pollution as well as water. It's going to be a challenge for the next, sure, yeah.
Even the pellets they say during transportation it gets into, yeah. So with all these challenges, do you foresee any challenges in polymer research going forward, or for polymer as industry, how it is going to move forward?
I think polymer chemists, like any other research field, all scientists are innovative, and once you push them to think and imagine of solutions that are outside of their normal thing, I think they would rise up to the challenge. And some of the interesting problems that people are handling is to deals with how to get best of both worlds. That means, you have plastics that are tough, strong, etc. But some of them also are very stiff. Okay, and so you have different kinds of use of plastic. And when you need something that is very stiff, let's say like steel or something that needs to reinforce it, they typically fall into a class of polymers called cross-linked polymers. Okay, they are highly cross-linked, and therefore they are very rigid, like bakelite, for instance. And when you make objects out of these highly cross-linked materials, they don't experience one interesting property called creep. That means you take a rod made out of, let's say, polyethylene, and you apply a stress on it. Over time, the polyethylene will sag like this, okay, like most other materials. And that happens because of slow relaxation processes in the system itself. So when polymer chains experience a stress, they will start to elongate, deform, change conformation, etc. And those processes, depending on the particular plastic, can be different rates. They can be very slow. But even if they are very slow, over 6 months, a year, they would gradually have moved to adjust to that stress that you've applied. And that causes the thing to reform, reshape. So in order to avoid that, you use highly cross-linked systems that are almost like ceramic. In a sense, they're very similar to ceramic. They will not creep. But those highly cross-linked polymers, unlike polyethylene and polyethylene terephthalate, they cannot be melted and reprocessed. So one of the big areas today is something called vitrimers. That means you install bonds that are exchangeable or reconfigurable. That means they can break and reform. And if you install those kinds of systems that can break and reform in highly cross-linked systems, then in principle, you can actually reprocess them like you process simple thermoplastics. Even thermosetting systems can be reprocessed. I think that's an exciting area. The other area that is going to see a lot of innovation in the area of plastics is that plastics, as we use it, typical material that are made of have several types of plastics that go into manufacturing. A good example would be the 5-layer bag that you use, plastic packaging that you use to put your chips and potato chips and so on. They have 5 layers. And they are all different plastics, and they are all having different processing temperatures, melting temperatures. So how do you process a mix of plastic? And many of the plastic waste that we collect is also a mixture of different types of plastic. So one of the big challenges would be on developing strategies, which would often require catalysis, I suspect. Yes. Strategies where you can reform materials with reasonably good properties using a mixture of several kinds of polymers. And that is going to be an innovation that would happen, I expect, sometime soon. Yeah.
Thank you. Actually, I could remember that we were working on Diels adder reactions for this reversible, 4+2 addition reactions. Thank you. Your, points were very much insightful. Moving away from this polymer research, some advice for our students. So in your opinion, what do you feel like students should focus on fundamental research, or they should focus on their upskilling so that it gives them a better, job opportunities?
This is probably the first question in the kid's mind today, What should I do? And, it's a difficult time for young children today because of this question. But I think to me, as somebody who's sort of experienced in the real academic area, I think there is no substitute for attaining fundamental knowledge. And the distinction between knowledge that is fundamental and knowledge that can be applied is an artificial one. So if you ask me, I would say if I want to apply knowledge, I first need to acquire it, correct?
Yes.
So I think this question is not whether I should focus on fundamental or upskilling. The question is on what should I know, what should I acquire, what knowledge should I know to enable me to, let's say, solve real problems of any kind. After all, I think most job opportunities are targeted towards solving problems using technology, right? Solving various problems, whether you're developing a product, whether you're developing a solution, whether you're developing a software, it doesn't matter. But the end is actually a problem that you're trying to address. So I think what students need to focus is two things. One is to, when you have an opportunity, acquire as much knowledge as you can. I sometimes tell my students there is nothing like a student life at IISc, for instance, because food is provided for, your vessels are washed, you don't need to wash your own vessels, everything is taken care of. All you need to do is really focus on studies. So this opportunity they would not get post PhD. They're in real life and they have to do other things as well. So I think acquire as much knowledge as you can while you're students. The second thing is not to confine yourselves to certain domains. Have an open mind and be willing to adapt. And that is a very critical skill that you would find very useful as we are changing very rapidly. So my advice would be to learn as much as you can. Don't set boundaries on what you should learn and what you shouldn't. You like something, you learn it. And you will never know what learning you've acquired at any time is going to be useful for you. Okay, that I can tell you from experience. In a sense that you think this is not relevant. Any topic, if there is a seminar, there's an opportunity to learn, you should be there learning. And you'll be talking, it'll be on a topic that you have no real direct interest in, but you would acquire something, some sense of where directions are, what is happening here. And in real life, these, after all, we are a collection of experience, right? After all, we are just a collection of experience. And what we rely on when somebody poses a question to us is we go back very quickly on all these experiences and then we try and put together a response. So I think in that sense, broaden your horizons, learn as much as you can. I think you would come back much more adaptable. Be willing to adapt. That's the key. Yeah.
Much needed advice for our students. Thank you so much. With this technology-driven world now, with all native technology, people as students with us, this mental health has become the topmost priority. I do see in your institution you have a well-being group and other club activities. So how do you see those activities helping students to grow as individuals?
The safety net that society had, in my opinion, is gradually getting fragmented. In other words, friends, keeping company with people, with technology, a cell phone, for instance, or gaming, or whatever else kids are involved in, their social network, is gradually sort of fragmenting. And this, I think, is one of the reasons why, after all, one way in which students, young children, young students, young adults, de-stress is through companionship. Activities that you do together, going to a movie, going and playing sports, all kinds of sports. And I think that we need to recapture that, space and get students involved in all these activities. I think The stress develops a lot more when you don't have people to converse. And so what IISc has done really is to create a formal platform where students can engage with sometimes professionals, sometimes counselors, and their advice would be largely this, and I think I remember telling my students, PhD students also, PhD is a very difficult period. It's not easy because the more challenging the problem you select, the greater the probability of failure. Okay, so I think it's something that they need to get used to failure, right? So if an experiment fails, you need to fall back on something else. So if you have sports that you like or some other activity, music and so on, you can at least on a day where your experiment failed, you go and beat another guy in badminton. It gives you a sense of, So I think that is important, to engage in multiple activities that keep a balance of what you say of success and failure on a balanced platform. You don't always feel down.
Seriously, you made me to think so much. The moment you said failure, the next thing came to my mind is now in this world, out of fear of failure in life, everybody seems to be running behind taking computer science or artificial intelligence, right? And then the media is filled with misinformation and disinformation. So what do you feel, we as science educators, should we need to reform our way of imparting science education, or any suggestions for us as future science educators in terms of redefining science education?
Yeah, that's a tough question because it's a long question, and as you have noticed in the last several questions, I tend to be winded. So let me try and confine. I just noticed that the time is just about over. Rethinking science education, I think, science is to be learned largely by observation. That's my belief, So in my own feeling, I feel that early science education, very early science education, that is in grade 1 to 5, there should be no formal teaching of science. Okay, this is really I've thought about this for a while, but I've never said this, but I think emphasis in the early period, it would be nice if emphasis was on arithmetic, language, and skills, and learning
Literacy and
science.
numeracy.
Yeah, and learning science by observation, where the laboratory is your outside world, right? So just challenge kids to ask questions about various things outside. And so if you develop a strategy where the early process is not formal science, but science through doing, watching, observing, hypothesizing, and all the formal conceptual foundings for science can be easily delivered in the 6th grade onwards. And I think if we do that, I feel we might have a lot more people who see the contact of science to everything around us. And I think if that relationship between science and its relevance to everything around you is developed very effectively, then I think would be a natural way to attract people into science.
Thank you. Absolutely, sir. Experiential learning, there's nothing that can beat. So just one last question. This is for we as women.
Sure.
I've been going through the list of awardees in maybe in SS Padnagar Prize, or even fellows in IA, Association for Science and all those things. I do see out of 330 people in chemistry, I saw only 5 or 6 women there. So what is your advice for young women who wants to be scientists? How can they navigate this system of getting funding for doing a better research, or how they can effectively contribute to the chemistry research?
I think this is another important area where a worldwide attention has been given to this problem of lack of balance and opportunities. And many measures have been in place for corrective action. It takes time. My own experience, I think, is I may have had just about the same number of female students as male students in my PhD thing, roughly similar. And our own admission into our department is also many times almost the same. So in biology, it might be even higher in women. Bioengineering, it might be lower. So erstwhile, there were disciplinary preferences, or maybe socially imposed, I'm not sure, but on what women should be studying. I think that is pretty much gone, at least in the cities. It's pretty much gone. Where, I don't think their women students, female students feel inhibited about taking any particular area. There are many role models who have performed exceedingly well in all kinds of discipline, including Sunita Williams, who has recently come back from space. So I think that conceptual, social sort of, I think, imaginary constraint, that's been broken. And in as far as representation in all these bodies go, there is a greater awareness and sensibility to requiring this representation. And I think in time it would happen. I think it's a very multi-parameter problem. As you know, as much as I'm very pleased to say that the equal number of students graduated, the number of them who have sustained, is a different question. So, that means there is a social fabric also, that fabric around which needs to be supportive to continue to be career oriented and have a career. That I think has not been as fast as education itself, and I think that needs to catch up. That means a supportive structure and social thought process has to adapt to this new state where support infrastructure exists for career oriented roles in both men and women. Yeah.
Hopefully, in next 10 years, can we expect some more
no question. Yeah.
contributions? So we as, me coming from education background, I would be more interested to know how to make science education fun, how to make chemistry fun for students.
That's a really interesting question that I've also thought of a lot of times. If I go back to my school days, I was more interested in physics than chemistry. There was no question. And the reason for that is all concepts that we learn in high school, like heat, light, vibration, friction, all these are directly relatable to real life experiences, And chemistry is taught in a way that is as if it's a separate science that with no relevance to many things. So I think the way to make chemistry fun, especially in the early stages, that means that's where you develop an interest in the science, is to bring the relevance and context of chemistry in the real world. For instance, RSC, Royal Society of Chemistry, has a book on various aspects of chemistry related to cooking.
Cooking.
What happens when you heat a boiled egg? What is the transformation that happens when something which is a liquid transforms to a solid? What is the underlying chemistry, And there are many things like that. So I think to bring context, how do you prevent iron, which is present in apple, from oxidizing? The color of iron, as soon as you cut an apple, it starts to become brown, right? So I think the point is to bring that link and get kids go back home and try these experiments with stuff that is available at home in the kitchen. Would probably excite them a lot. What is glue? Why is atta rubbery? And so many things. So many things which are relatable. So I feel that chemistry books have never been written in that way. And I think if you bring that connection to real life experiences, it would make it a lot more fun. And so many gadgets today, displays, light bulbs, so many things involve fundamental processes, which are explainable. So I think if we bring that, we can excite kids more about chemistry. Yeah.
It goes well with our, program goals of BSc B.Ed as well. And thank you for reiterating the point. The other thing I'm more interested to know is always there is this tug of war between research and teaching. So how to balance teaching and research? And the follow-up question is also, wherever we go for, research conferences, there seems to be more emphasis given to the research what academicians do than what teaching methods or what pedagogies they use in their classroom. So what is your opinion, sir?
Very true. I think this conflict is like applied and fundamental research. The boundary between teaching and research is a little artificial. So I feel most researchers, if they need to be effective, it would greatly help if you engage in teaching. Teaching is not a process where the teacher delivers alone. Teaching is a process, is an experience where the teacher engages with the student and relishes the fact that the student has understood. So it is a two-way process where you engage and you receive back the feedback from the student. Another very important thing is that while teaching, many of the concepts that you yourself might not have completely understood becomes clearer, because the attempt to explain something in a way in which the student can understand forces you to think of the topic that you want to explain in many ways outside of what you normally do. Okay, how do I get this concept clearer? What analogies can I use to explain this? And that process helps clarify concepts. And I've always enjoyed teaching because it has always taught me something that I hadn't thought about earlier.
Agreed.
So I think, and many times, research problems can be embedded in these explanations that you provide. Experiential, based on an experience, I'll tell you, an undergraduate student, I was teaching a course and he wanted to, I was explaining something, the Carruthers expression, for instance. He said, "Sir, how can I actually test it? I want to come and work in your lab in the summer to actually show that Carruthers expression is valid." So that forced us to design a research problem where it's not a research problem. Design the problem in such a way that using simple technique like NMR, you can get the degree of polymerization and you can also get the extent of conversion,
Yes.
which
Otherwise,
required a
we
little
study
bit of
theory.
innovation.
Yeah.
And I think so. The point is that teaching actually also constantly is giving you feedback that enables you to do research better. Okay, so I think there's no dichotomy. I think teachers need to be teachers at college level, I think, would be enriched by engaging a little bit on research with whatever they have, but small research problems. It just gives a feeling for both the students and in higher learning universities and where the focus is more on research. It helps enormously if you're teaching. And this conflict is there only in some countries. In the US, for instance, most universities, all the teachers not only teach, they also actively engage in research. Yeah.
Regarding the dichotomy in conferences.
Oh, that is, most conferences are research focused, unfortunately, Muthulakshmi. Yeah. There has to be a separate session where the focus is on education. I think there are very few conferences that I've attended where both of them are discussed, So I think really, because that's the nature of the conference. Journal of American Chemical Society has a separate wing on chemical education, right? Separate subgroup, which hold separate sessions on education. Yeah. That's something we should do in India, I agree. And I think CRSI is actually having
Yes,
that.
yes.
Yeah.
We had one recently
Right.
in Madurai where we requested to add chemistry education there. But I think much more would be
Correct.
helping.
True, absolutely true.
Thank you so much, sir. Thank you so much for your time. And your insights will definitely help us and our students to do well in our life. Thank you so much, sir.
Thank you very much.